My name is Andrej. I work at Chainlink Labs, basically building Chainlink, which is a blockchain services platform. If you're already not familiar with it, basically on whatever blockchain you're working, we have all the services and tools for you to just combine it and do your thing. So it's like a platform. So for example, for cloud computing, you have AWS. For blockchains, you have Chainlink. The reason why I'm here today is because these lovely people from ETH Belgrade called me to talk something Solidity. So I'm not going to shill any project on or any protocol or whatever. This is a 2-year-old tweet, basically a write-up. I had a discussion with my team about BAYC NFT collection, basically why this orange monkey to transfer from one externally owned account to another externally owned cost more than to transfer this green with this red hat or whatever. That'll be our main topic. Basically, if you work with me, because I work with some of you guys, and you saw this tweet, don't ruin the presentation. But the idea is basically to have like a dialogue instead of monologue. Basically, imagine that we are all like the same Solidity team or dev team, and we want to figure it out why this thing, to transfer this thing, cost more than to transfer this thing. Both transfers happened on Ethereum mainnet in less than 1 hour. Cool, that'll be it. I'm gonna scroll through this thread. So basically, any ideas? What will be your starting point to figure it out why the cost was different? Because this was during the bull market, prices are high, so like it really matters like if it's like $1 or 5. Ideas? Yes, over there.
Perhaps you were touching different bits of states or manipulating state, and it was a different state from the first transfer to the second transfer, so some bigger operation had to be done?
Yeah, cool. So this is actually a really good guess. So what I'm gonna repeat just for the audience online, basically what James said was maybe during these two transfers we touch different storage variables or different parts of storage, and because that potentially can cost different amount of gas in units, can result in higher thing. One thing that I didn't mention is that this orange thing, its ID is like 6,521, while this one is like 724. So does anyone think that matters? I see a couple of nod heading. Do you think why it matters? The ones who nod their head like, yeah, that matters, like ID matters. Maybe why? Yep.
The number is larger, so there are more ways to display the number.
Yeah, totally valid guess. We had that as well. Like the number is larger, so consumes more like bytes or bits under the hood. We'll see when we swap this to hex representation. So maybe because of that, this costs more. Do we have any more guesses? Maybe before we continue. What else? What else? Yes.
I have a question.
Question? Yeah, sure.
When you say costs more,
yeah,
you're talking about like native token, or you're saying, okay, this is like this amount of gas, this is this amount, because it's different time periods. So
yeah, sure. So I'm going to repeat the question. Question is, are we talking about gas units or the actual fee? We're talking about gas units. So we had that discussion as well. So there was like one junior guy says like, yeah, but you transfer this at like 3 p.m. This was at 4 p.m. Like gas prices were different, like that's different, but no. So we don't care about gas fee at that particular moment. We care about gas unit. And to be more precisely, to transfer this NFT with higher token ID, it costs 12 gas units more than to transfer this one. Okay. Actually, I should start with this one. Do we all know what an NFT collection is, like technically? Can someone tell me really quickly what an NFT collection is? Yes?
It's a smart contract on Ethereum which contains an array connected to addresses.
Yep.
To URLs that are pointing to the picture.
Yeah, it's a smart contract on this one particular Ethereum mainnet, which means that the code is the same. All of these different monkeys or whatever are just some as you said, like objects in array, but we can interpret it like that. Basically, what I want to say is the smart contract is the same, so the transfer from function is the same, right? And that's why James had a good guess. Maybe we touched different types of storage. Okay, cool. Before we have a couple ideas. So we have storage access, we had length of the ID, and we have had a question about gas units versus gas prices. We said, yeah, this is on gas units. Okay, what next? So let's now dig into it. What will be our next step? Well, our next step will be to actually go to transaction hashes, right? So I put like 2 transaction hashes for these 2 transfers, and we can see them here. Let's do here. Okay, so do I need to zoom it a bit, or you can see it? Zoom? Yeah, I'm gonna zoom. Oh, I clicked and had. Okay, first thing, just let me say when to stop. Good? Okay? Okay, cool. Oh, this is the same. Okay, cool. So first, if we want to figure it out, the James solution, actually approach, about touching different types of storage, where should we look, right? This is Etherscan, but I guess you're all familiar with it. And if I scroll down a bit, we can see this is the transfer of a orange one and the transfer of a green one. And as I said, these are the fees. So we can see, okay, gas price different, but we don't care about that. So gas price and gas price, we don't care about that. We're caring about gas units. So if you want to see gas units, we need to, let me see. Yeah, we need to click more details. Okay, cool. So I'm gonna open more details, and we're gonna focus on this part now. So we can also see that transfer from to exact functions. So gas limit and gas usage by transaction, we can see that this one consumed this amount of gas units, and this one consumed this amount of gas units. And the difference is 12. So we're looking for those famous 12 gas units to see why they're different, because the same smart contract, same functions, same blockchain, everything the same. Just the IDs or the actual NFTs are different. Okay, cool. Now we want to start with James solution. How should I now, you know, like I only have these 2 transactions, nothing more, nothing less. So what should I do to figure it out? Which storage slots have I touched, or not I, but the transaction during these 2 transactions? What should I do now? Any ideas? Please raise your hand, and we can continue. Yeah.
Trace the transaction.
Exactly. We should trace the transaction. Does anyone not know what the tracing of transaction is? Feel free to raise your hand, I'll explain anyways. What he meant by tracing, like tracing a transaction.
I don't know.
You don't know? Okay, cool. Fair enough. So tracing a transaction means that we want to follow every single step from the moment you sign up, sender sign it, to the moment of the transaction actually being included in the next block and finalized on blockchain. So there's like multiple steps involved. First and foremost, when you're talking about transactions, does anyone know how much, because this is Ethereum mainnet, how much does a transfer of any amount of ETH costs on Ethereum mainnet? Yes?
21,000.
21,000. So we're starting with 21,000. Okay, so transfer of ETH, like a native coin for paying gases on Ethereum mainnet, costs 21,000. So we know that we must start with 21,000. And then there's some extra costs involved. When working with smart contracts, basically we're gonna populate this input data or call data field. This call data over here will be empty for native transfers of ETH, but when work with smart contracts, we will have something like this. This is decoded input. Original input data is something like this. It's a giant hex number, basically. So that giant hex number tells us a lot. if we know how to decode it. And also, the receiver of a transaction tells us a lot. So if a receiver is a smart contract and this call data is correct, then that smart contract will execute some computation which will cost some gas. We all know why that costs more? No? Yeah, because Ethereum is a decentralized blockchain, decentralized network, so you need to have an incentive to participate in the network. So the more work your node or computer does, the more you need to be rewarded. That's simple as that. So transferring an ETH or doing some infinite loops, or not infinite, but some huge computation on smart contract is basically not the same. So it costs more. Okay, cool. Do we all know how to decode, how to read this call data at least?
We don't.
We don't. Okay, cool. When we start with call data, we first need to take a look at these 4 bytes over here. And these 4 bytes over here, 23B872DD, 23B872DD. That's not a coincidence. 4 bytes at the beginning on call data basically tells the Ethereum virtual machine which function to call. So if we, again, decode this input data, what I does it? Let me see. If we, this default view, we can see that, okay, cool. We can see that, again, here is this hex number, 23B872DD. So this is a function selector for transfer from function which accepts 3 parameters, 2 addresses, and 1 uint256 on this BAYC smart contract. So function selector means that now EVM will jump through bytecode to find the exact function selector and then to continue with the computation, right? How we get this number? Basically, we are gonna get the function signature. That means like transfer from address uint256. Gonna hash it with catchup256 hash, which is a hashing algorithm on Ethereum mainnet, and we are gonna get from that value the first 4 bytes, and that's it. And does anyone know why is this important? Actually, I said you're gonna you're gonna jump from function signature to function signature to function signature, etc. Is this important in terms of like gas consumption? Yeah, Igor.
Yeah. So basically, the EVM is going to look for the function signature that matches this. For the function that matches this exact signature. So the more it loops to find it, the more gas is going to.
Exactly. So he said basically the more, so EVM will go jump from function signature to function signature to function signature until it finds the right one, or it will just revert if there isn't another one. So each of these jumps costs 4 gas. So the more jumps, more gas. So we have 21,000 plus 4 plus 4 plus 4 plus 4. Well, let's continue. Okay, so that's already like 16 more gas, right? Is this relevant for our use case? No, because they're the same 2 functions. Okay, let's trace it out. So for tracing a transaction, there are a couple of good websites. I'm not gonna shill the domestic product, but that's the one that I'm using. Oftentimes that's obviously Tenderly. So should I zoom this a bit, right?
Zoom more on Tenderly.
The logo? Okay, cool. So yeah, Tenderly, great guys. They created this basically Swiss knife debugging tool for all EVM and I think now in non-EVM blockchains. Nevertheless, what we can do here is that we can actually, as James said, trace the transaction, see all the details about these 2 transactions. So basically, let's zoom it a bit. So what do we have here? We have all the details from Etherscan. Receiver is the smart contract, blah, blah. And then this is the actual trace, right? So these are all the functions called that happened, both internal and external function calls for this transaction and for this and for the other one. Okay. So what we assume is going to be the same is the function trace, right? Because transfer from function is the same, we expect all the internal and external calls to be the same. And like, if we quickly analyze this screen, is that correct? Yeah. Okay. So we agree on that. But what we're specifically looking are actually storage accesses. Why storage is important when working with Solidity? And this is a really important question, actually. So to roll back a bit, I'm going to talk for like 2 minutes. So to start with, Solidity is extremely easy. Solidity is extremely easy language, extremely readable, extremely easy to write. Like syntax is JavaScript-like. Under the hood is kind of like C++ or some kind of structural language because it is written in C++. And the only reason why it exists is because it produces so tiny bytecode, and it's more cheaper than to write in, I don't know, like TypeScript, Rust, or whatever. There are also other EVM-compatible languages like Viper, FE, Huff, and others, but they're not really a competitor to Solidity because their ecosystems are really small. Viper is probably the second best, but 20 extremely smart people is not an ecosystem, basically. So Solidity is like a dominant player at the moment. Not because it's like the greatest language ever. So just let be real. So to start with Solidity, it's extremely easy, right? But to master it is extremely hard, actually. So like Pareto principle really applies to Solidity. Like you'll learn like 80% of the language like this, maybe in the afternoon. But to really master and craft those final 20% percentage is hard, and it gets harder and harder. Why? If we have like cross-chain, so if you're typing in Java, you need to know how Java virtual machine works under the hood if you want to write an efficient code. Ethereum virtual machine, EVM, is, many smart people told me, I'm not that experienced, I'm still young, that this is the most simplest virtual machine they ever saw. So simple language, simple virtual machine, all good. But the thing is that we need to learn how that virtual machine works under the hood, and also this especially is important for like cross-chain applications. We kind of need to know all the tiny details of a blockchain or underlying blockchains under the hood. So the most obvious example is probably Ethereum mainnet has like push zero opcode. Majority of layer 2s do not. So that's the difference, right? So yeah, to sum it up, like to learn Solidity, to start with it, it's extremely easy, but to master it, you kind of need to know all these tiny details. And we are now tackling those tiny details. So when it comes to Ethereum mainnet, right? That happened, I think, like 2 or 3 years ago. There was like probably 3, Berlin hard fork. So I'm going to share a repo actually with you. I think I have it over here. This is the repo I used to learn all about Berlin hard fork. Where is that? Yeah, here it is. So it's called Berlin gas costs. So let's see what are the differences actually. Basically, before Berlin, we had opcodes that were like extremely straightforward. So if you're writing or reading to memory, that's extremely cheap. If you're reading and writing from storage, that's expensive. So what you want to do is to do really ugly thing is that if you need yours to access storage, that was before Berlin, multiple times, what you will do is you will copy the variable from storage to memory, which is extremely ugly piece of code. You have like two unnecessary lines, and then you're gonna read from that memory until you need to write something back to storage. So mload costs 3 gas, mstore costs 3 gas, and that was it. Sload was always 800, which is a lot. So just to read one thing from a storage will cost much, much more than to read from memory. And when it comes to store, there are a bunch of different options. After Berlin, well, memory kind of remained the same through 3, but we got a change regarding the sload. So the first sload costs 2100 gas, while each single slot costs like 100 gas, because now we have like the terms of cold access and warm access, right? So it got cheaper, right? So what the new gas golfing technique became to pack your variables in structs or declare them in a way that they will fit in a storage, right? So if you have like address, boolean, and number, you will not, and uint256, you will not do uint256 boolean oh, that's a poor example. You will not do address, uint256 and boolean. You will, for example, do address and boolean because they'll fit in the same storage slot, and uint256 do another. You already probably know about that. But the reason why this change is also important is because in some other blockchain you don't have Berlin, you don't have like warm and cold access. But for this one particular, if we take a look at this thing over here, so in Berlin we also got the thing that if we have like something written in a storage, but we're changing the value back to the default one. So for numbers, that's 0. For addresses, that's address 0. For booleans, that's false. And for strings, that's empty strings. I think bytes, empty bytes, whatever. The thing is that you will get some kind of gas refund, right? Why is that important? Because now nodes in a blockchain, in Ethereum blockchain, doesn't need to store that extra info in their internal database bases, so it's cheaper for them. So you get like a gas refund. So what we can do now? We can trace the function signature to see storage accesses, right? To see what James said. Because of these different token IDs, maybe like did we, I don't know, like access some particular storage, which was like, I don't know, like, we'll see. That's a long shot actually because the difference is only 12 gas, but we'll see. And we can look for gas refunds. So we can look for gas refunds. Gas refunds are important. So for example, if I you know, like, I don't know, like if there is in that smart contract somewhere to be written in storage, this is also a long shot, how many NFTs I do have, and I now transfer it and I don't have any, so now it became 1 to 0, for example. This is not an example, but you get a point. So maybe something wrong with that. So what I'm gonna do now is, and also, yeah, I forgot, but where is that? For opcode stuff, like EVM codes is extremely good website. So if you want to bookmark it or whatever, like you have Playground, everything like opcodes. So what I was talking about for interconnection slow, but for any given opcode, you have yeah, here it is. So for any given opcode, let's say sload, here is if I expand it, bunch of details, etc. Never mind. We are kind of out of time, so I'm gonna speed myself up. So in standardly, you can, and let me see now, it's really big, to find, like this is the full trace. We can, yeah, here it is. We can select storage access. So now we have storage access, and you know, you can see with red, bunch of S loads, red S loads. How can I swap this? Maybe up. I don't know. I need to. Okay. No. Storage access. Let's refresh this thing. So, long story short, because we were kind of running out of time, we checked for storage access, and the thing is that there was no like different storage included. So for both transfers, they used exactly same set of opcodes, exactly the same. When it comes to storage, they accessed exactly the same storage slots. So that wasn't the issue. The next issue, which I was talking about, is about gas refunds. So in Tenderly, if you click on this gas profiler, you can see the details about gas usage for this transaction. I need to now, yeah, gas profiler. So what we're interested in is our gas refunds. So if you click on this tab, we can see gas refunds. So from something to default to 0. And is this the issue? No? Yeah, the same values. So 14,400, 14,400. So gas refunds again. Great. We save some gas, but that's not the issue. Okay, what's next? Do we have any ideas? Like what can also what can also be the reason why we have that difference of 12 gas? Yes?
Was the upgrade in between the two transactions?
What do you mean by upgrade?
The upgrade you talked about?
No. Was the hard fork happened in between those transactions? No. Highly likely, good shot, but yeah, no. And it'll probably cost much, much more because, like, yeah. Yes?
There's something we call the
Something with call data. Okay, this is actually a really good shot because if you are transferring ETH like from one externally owned account to another externally owned account, we said it cost 21,000. And I can put whatever I want in that call data, and if it's like a legit thing, my receiver, aka smart contract, will know how to interpret it. But I can actually show that to you now. Let's do like a quick demo. So let's switch to Sepolia. I hope you can see this. So I'm gonna send just a tiny, so I'm gonna just swap with my other account, doesn't matter. I'm gonna send like a tiny bit of Sepolia, so this is extremely tiny. I hope you can see this. I don't know if I can zoom it a bit. No, I can't. And optionally, I'll put some hex data. So this is call data here. I'm gonna put it manually, so let's say 1, okay? And if I click next, how much of gas in units will this transfer cost? 21,000. Anyone else?
Plus something a little bit more.
Why? So you said 21,000, you said 21,000 plus something.
But you added hex data.
But why is that relevant?
I mean,
Is it relevant? Let's check. What's your guess? Is it relevant because I add this tiny hex number in call data?
Yes.
Yes, why?
I think call data costs two gas per byte, no? Or something like that.
So you said it'll cost 2 gas more. It actually costs this amount of gas. Actually 16. Why?
Is it going on block? Is it going on chain?
Call data is visible on chain, yeah. But it's not like it's gonna be stored on a block. But yeah, you get a point. Like validators will need to process that extra call data, no matter if it's used or not. So your guess was actually correct. It gotta be something with call data. But what? Okay, cool. If we go back to original transaction hashes, how can I see the actual call data? As I said, here, original. Okay, we are looking for something unusual here. Can someone spot a difference or something? Excuse me? Length is different. I don't think so. I think it's just the font. Excuse me?
At the end,
Yeah?
3 numbers, and on the left you have 1. So you have 0 on that one spot.
Yeah, but that's the same byte. So byte is actually 2 characters, so that's like 2 D4.
Okay.
So yeah,
Search more.
let's search more. Okay. But do we know what we're searching? Like this is kind of like needle in a blast, right? Because like, okay, we'll find some different. Okay, let's stick with these 4 characters. Okay, 1979 02 D4. What's the difference, right? Why do we care about that? Can someone tell me?
Storage.
Excuse me?
Storage per type.
This is call data. So call data is not a storage. So you have like 6 different places from where EVM can read stuff. So you have storage, memory, logs, call data. So they're all different. So storage is a lot more expensive. So this is just, we're dealing with call data because we're looking only for 12 gas units. Yes?
Both options involve the same smart contract.
Yeah.
Same code, same choices for storage.
Yes,
So it wouldn't
yes.
make sense that it's there.
So it will be?
It wouldn't make sense if they're invoking the same. Maybe it has something to do with the sender transaction.
Okay, cool. So we have another idea, maybe something with sender transaction because he is convinced we have the same contract, same function, same set of opcodes. So it it's doesn't necessary with the call data. Okay, cool. How many of you are convinced that's something with call data? Okay, couple of hands. How many of you think it's something else? 1, 2, 3, 4, 5. Okay. For you think it's something else. Can we have more ideas? Because like we have like, oh, we're out of time already. So I'm gonna speed it up. More ideas to ask?
I have a question, to be honest, I'm not so proficient in.
Okay, can we do questions after I?
No, but I have a question that is a guess.
Okay. Oh, it's a guess. Okay.
Yeah, if you go with the trace,
Okay.
if I go and check if For example, I saw in the trace that you have a function that checks does the token ID exists.
Okay.
That works, and the computing part, you just find some location of
Yeah.
token ID in the storage. My guess is that it can cost some gas a bit more.
Yeah. So what he said basically was, if we go back to a full trace, and if there is a check for if this token ID exists, maybe there will be in different places in storage. That's not it, because again, storage here now that we know is like only 12 gas units. Storage is much more expensive. Yes. No? Just a hand. Okay. Any more ideas?
Priority.
Excuse me? Priority.
Block position.
Priority and block position. Yeah, that's not it. Okay. Anything?
Transfer to contract.
What do you mean by transfer to contract?
I mean the destination of this transfer.
Yeah, destination in both cases is the same. It's the address of BIYC smart contract. So whenever you want to call a functional smart contract, you're gonna perform the regular ETH transfer, like a regular transaction, 21,000. The destination will be the address of a smart contract, and then you'll put something in a call data, like I did. Any ideas with call data? Should wrap it up. Okay, cool. So if I go back to my earlier transaction over here, when I put that hex number in a call data, we can see now that the transfer is not 21,000, it is actually 21,016 because of that extra stuff. So what we did is we compared, actually I compared call datas of both these transactions. So if I open this thing, and I'm gonna zoom it a bit, if I can, there is one anomaly over there. You can see? We have one byte, one extra all zeros byte. Okay? This is an anomaly, right? Because here, if you scroll back, function selector, this is an address, you can see. So whenever you see 20 bytes, so whenever you see like 20 bytes on the right and a couple of leading zeros, that's probably an address. So an address, and then this third thing, these are token IDs. And that was actually a valid guess, because this number is greater than this one in terms of hex, right? And that was our premise at the beginning with Igor's suggestion, like maybe because their token IDs are different, that will somehow mess the call data. The trick is that wasn't the case because of these two. So if here was like another zero, that will make a difference. But no, this is just a regular hex numbers, hex values. So if we go back here, basically the thing is that because of these different addresses, so this is the address of a sender, so from address, this one has like one extra all zero byte in it. And the answer is always, when it comes at least to Ethereum mainnet, is always in yellow paper. So if I now collapse this and go to yellow paper and take a look at this, we can see that, give it a bit, we can see that cost of storing data in call data is different. So if we have 0 byte, it costs 4 units of gas. If we have non-zero byte, it costs 16. So 16 minus 4 equals difference of our two gas units, 12. And yeah, that's it. That's how we found it in Ethereum yellow paper. And yeah, that'll be it for today's talk, dialogue.